sometimes facts about connectedness can be used to show negative results, the impossibility of something happening. So here's an example. There is no one-to-one continuous function f from the plane to the real line. Now it's sort of intuitively clear because what that would do is it would take the plane and somehow push it into the real line. So it seems unlikely that this could happen, but that's not an argument. But we can use connectedness to show this. So first of all, since R2 is connected, its image, whatever that is, in the real line is also connected. Now, we already discovered what connected subsets of R happen to be. They are the intervals of one kind or another. So therefore, f of R2 is an interval, and it cannot be just a point, because if it were, that would say f mapped all of R2 to a single point, and so it would not be one-to-one. So it's not a single point. By the fact that f is one-to-one.
So we just kind of assume that's continuous and one-to-one, right? So
yeah, one-to-one continuous function. Okay, so that means there are at least two distinct points many more, but at least two distinct points, A less than B. So let's take any intermediate point, C. Now, because the range is an interval, that point C must be f of something. So there is an x0 in R, so that f of x0 is equal to C.
R2.
Thank you. R2. So here's the picture. Here's the plane. There's some point x0, and it's being mapped over f takes it there. We don't know where x0 is, but it doesn't matter. Now, to derive a contradiction, let us remove those 2 points, respectively, from R2 and R. So I'll take out the point x0, and that maps to R C removed. But the point is that when I take x0 out of the plane, it's still a connected set. Because I can connect any 2 points in the plane without x0. If necessary, I will just go around it. So no problem there. But the point is that the range of f has been disconnected. Because there were values to both the left and the right of C, when I take the point C out, this is no longer a connected set. So I would have a continuous function that takes a connected set to a disconnected set. That's impossible. So this is a contradiction. And what did it contradict? Well, the assumption that there could be such a function. So there is no such function. So in this way, we find that we can distinguish certain spaces. So R2 cannot be the same as R. We had a one-to-one onto continuous function where we just showed that there is no such thing.
So this argument, if you remove the one-to-one part on f, does that mean the only function that actually works is just a constant function?
No, what we could do is we could take, in coordinates, we could take point x comma y to x. And what that would do is squash the plane down to the real line, because it's far from one-to-one.
Is this new function still connected? Not connected, continuous?
Yes, whenever I restrict a continuous function to a subset, it remains continuous, just because of the definition of continuity. Another example, this has to do with path connected. So if x and y are path connected metric spaces, then so is the Cartesian product x cross y. So we just have to show that there's a path joining any 2 points in the Cartesian product. So take a pair x0, y0 and x1, y1 in x cross y. So we have to construct a path knowing that x and y have that property. So what we can do is, in the plane, we could move vertically and horizontally to get from one point to another. We can mimic that here. So what we can do is take a path from we're simply freezing the second coordinate. And once we get there, we can then join it to a path that takes us from x1, y0 to x1, y1. So the picture is this. Here's x0, y0. Here's x1, y1. And basically, the path connectedness of the two components says that we can move horizontally and we can move vertically with the path. So we would first of all go over to the point x1, y0. And then we would go up like that. So the Cartesian product of connected spaces is connected, pathwise connected. And then one final result in this topic.
Why are you going for an intermediary point? Isn't it easier to just define a component-wise function?
I could do that. If I have a function from x0 to x1 and a function from y0 to y1, I could simultaneously follow it. But both things come to the same. Okay, so one last result in this area says the following. We all know the intermediate value theorem on the real line. It's a variant of that. So let xd be a connected metric space. Let f from x to r be continuous. If f takes values a less than b, then it takes any intermediate value c in the interval. So in the real line, the picture that goes along with this, if we have these two values somewhere, and we have a c in between, then somewhere the curve has to cross that line and take value c. But it works for a very general domain. Any connected metric space will do. And the reason for it is this. It's essentially the argument that we had in that example with the one-to-one function. Fix a c in the interval ab. If f never has the value c, then x interval minus infinity to c, union the inverse image of c to infinity. We won't miss any points in x by that because none of them gave the value c when we applied the function f. But both are non-empty. Since the values a and b are in the range of the function f. But now we've managed to disconnect x. And so that is a contradiction. Right, so that completes what I want to say about connectedness. The next topic I want to look at is this. Something called Banach's contraction mapping principle. And what it has to do with is functions of a metric space to itself and when you can expect them to have fixed points. Once we've derived the theorem on that, then we'll look at applications. It's a very useful result and gets used quite a lot in different contexts. So let's begin with a definition. So let XD be a metric space. Function t from x to x is called a contraction if there is some number c less than 1, and that's important, strictly less than 1, so that the distance between tx and ty is less than or equal to c times the distance from x to y. And that's for all x and y in the metric space.
The c less than 1, does the c have to be greater than 0?
Oh, yes. example of a contraction. T maps from the real line to the real line, and T of x is equal to x over 2. Then if I have any 2 points, T of x minus T of y is x over 2 minus y over 2. And so the distance between T of x and T of y is the absolute value of x over 2 minus y over 2. And in this case, this is equal to 1/2 the distance between x and y. So here we can take C to be 1/2. So that's an example of a contraction. And when you look at the definition, what a contraction is doing is it's saying, given any 2 points, when I apply the function to it, it brings them closer, but definitely closer by a factor of C less than 1. So it's moving any 2 points closer to one another. So this one is not a contraction, even though it looks like it might be. Let's define T of x to be 10 to the minus 1 of x, for x in the real line. So if you want to look at the distance between T of x and T of y, should be a minus sign. One way of deciding whether something's a contraction is to apply the mean value theorem. So T of x minus T of y is the absolute value of tan to the minus 1 x minus tan to the minus 1 y. And that is equal to the derivative of tan to the minus 1 x evaluated at some point c times the absolute value of x minus y. So there we're applying the mean value theorem. It says the difference between f of x and f of y is the derivative at some intermediate point times absolute value of x minus y. The derivative of inverse tangent is 1 over 1 plus x squared, so this is 1 over 1 plus c squared times the absolute value of x minus y. Now we don't know what c is. 1 over 1 plus c squared is always less than 1, less than or equal to 1, but here, let me make this for x in 0 infinity. Over 1 plus c squared is less than 1 on 0 infinity becomes arbitrarily close. To 1. So there isn't a single constant less than 1 that I can put in here to give me a contraction. So this function does move points closer together, but not by a fixed factor. When you get down close to the origin, where the derivative is very, very close to 1, these points are not moving together very fast. So this does not count as a contraction. So here's the theorem. Which is 3.9. So this is Banach's contraction mapping theorem. For this we need completeness. Let X be a complete metric space, and let T from X to X be a contraction then T has a unique point at 0 satisfying T of x0 is equal to x0. So this is called a fixed point for a function. When you apply the function, it doesn't move the value. Just get the same thing back again. So there's two ingredients here. First of all, the existence of such a point, and secondly, the uniqueness. So since I've insisted that X should be a complete metric space, you can guess that we're going to construct this point as the limit of a sequence. And the completeness will guarantee the sequence is in the space. So let C less than 1 be the contraction constant for T. So we will construct a sequence xn with an arbitrary choice of the first one. But once I've chosen the first one, I'll get all the others by applying T successively. So x2 will be T of x1, x3 will be T of x2, and so on, and in general, xn plus 1 will be T of xn. yes, because t brings x back to itself, and therefore it makes sense to apply the function again. So what we're going to show is that this is in fact a Cauchy sequence, and the limit of it is going to be the point that we're looking for. So we will show that this is a Cauchy sequence. Now, we don't know where t sends x1, so we have no way of measuring the distance between x1 and x2. But after that, we do. So, notice that the distance between x2 and x3, well, we got x2 by applying t to x1, and we got x3 by applying t to x2. So this is the distance between t of x1 and t of x2. And using the contraction property, that is less than or equal to c times the distance between x1 and x2. So no matter what x1 and x2 are, x2 and x3 are closer together than the original pair. Well, do it again. The distance between x3 and x4 is the distance between t of x2 and t of x3. That's at most c times the distance between x2 and x3. But we already estimated that in the previous line. That's going to be at most c squared, the distance from x1 to x2. And I'll do it one more time to establish the pattern. When I come to the distance between x4 and x5, that's the distance between t of x3 and t of x4, which is less than or equal to a constant times the distance from x3 to x4. And the previous line said that was c squared, so this is less than or equal to c cubed times the distance from x1 to x2. So each time we do such an estimate, we pick up another factor of c, and so in general, we will get the distance from xn to xn plus 1 will be less than or equal to c to the n minus 1 times the distance from x1 to x2, and that will work for n greater than or equal to 2. With these things, it's always either c to the n or c to the n minus 1 or c to the n plus 1. So you just have to figure which formula works with the initial examples. So for example, when n is 3, we should get c squared. So that's why it's n minus 1 here. So now we have an estimate on the distance between consecutive points. To show it's a Cauchy sequence, that's not good enough. We have to have estimates between xn and xm. So if n is less than m, the distance from xn to xm, using the triangle inequality many times, we can estimate that as the distance from xn, xm plus 1, plus the distance from xm plus 1, xm plus 2, plus, and then the distance, the last pair will be from xm minus 1 to xm. Now if we use the estimate that we have at the bottom of the other board, this will be less than or equal to, all of them will contain a factor of distance between x1 and x2. So this will be distance from x1 to x2 multiplied by c to the n minus 1 plus c to the n plus c to the m minus 2. That's less than or equal to the distance from x1 to x2 multiplied by c to the n minus 1 and now it only makes it larger if I let the series continue indefinitely. And that's a geometric series, 1 plus c squared, and it's equal to 1 over 1 minus c, and that is because c is less than 1. Otherwise, it wouldn't be summable. And so this is equal to the distance from x1 to x2 times c to the n minus 1 divided by 1 minus c. And this goes to 0 as n goes to infinity. So far enough out, any 2 points in this sequence will be arbitrarily close together. So therefore, the sequence xn is Cauchy. By completeness, this converges to some point x0. So I claim that this is the point that we're looking for. So given epsilon greater than 0, we can choose capital N so that the distance between xn and x0 is less than epsilon for n greater than or equal to capital N. So that's the convergence of the sequence xn to the point x0. Now, if I apply t, that makes the distance smaller. So then the distance between txn and tx0 is less than c epsilon, which is less than epsilon, n greater than or equal to capital N. But t of xn is just the next point in the sequence. That's xn plus 1. So the distance from xn plus 1 to x0 is less than epsilon t of x0 is less than epsilon for n greater than or equal to capital N. And what that says is that the sequence xn converges to t of x0. But it was already converging to x0. We get the fixed point that we're looking for. We get t of x0 is equal to x0. So that proves the existence of a fixed point. Now we want uniqueness. So suppose that we have two of them. So suppose we have two fixed points x0 and y0. Well, if we apply t to those fixed points, because of the contraction property, the distance between t of x0 and t of y0 is less than or equal to c times the distance between x0 and y0. But being fixed points, this says that the distance from x0 to y0 is at most c times the distance from x0 to y0. Well, the only number which is less than or equal to c times itself for c less than 1 is 0. So that implies that the distance from x0 to y0 is 0. And so these two points are equal. And that shows that there is only one fixed point. Therefore, the fixed point is unique. We have just a couple of minutes left, so let me show you that having completeness is essential here. define T from 0 infinity to 0 infinity by T of x is equal to x over 2. Then the absolute value of T of x minus T of y is 1/2 the absolute value of x minus y. So this is a contraction with c equals 1/2. I've mentioned this example before. So x0 is a fixed point, then we must have that x0 is equal to 1/2 x0, which implies that the fixed point is 0. But this is not in our metric space. So here's an example where we can have a contraction, but there is no fixed point. And the reason that this failed was we could have gone through the whole proof up until the moment that we said the Cauchy sequence converges. Here the sequence would be tending to 0, which is outside the space. So this fails because 0 infinity is not complete. Of course, we could fix that problem and consider T mapping from the closed interval 0 infinity to itself. Then there would be a fixed point, and it would be the point 0. But it does illustrate that you cannot rely on having a fixed point if your space is not complete.